Hello everyone, welcome to Codedynamics. In this video, we are going to use a tool called cfMesh to generate mesh for OpenFOAM. We are going to use this geometry which you are seeing on the screen, which is like a spacecraft. I have downloaded this model from a website called fetchcfd.com and it is free to download. You can just create an account for yourself in fetchcfd.com and you can download this model. I will give the link in the description. So we will see what is cfMesh and how to use cfMesh to make a mesh for OpenFOAM. If you have already installed cfMesh, you can jump right into this video and follow it. If you have not, then you can visit the website of cfMesh, which is cfmesh.com, and you can download and install cfMesh. If possible, I will try to make a video for installation of cfMesh. If I have already made, I will put the video link in the description. Otherwise, please wait. I will soon upload it. Okay, now let's look at how to make the CF mesh and all the process which is involved. Okay, now when you download this model, it will be in STL file. I have already downloaded the file. So I will open a paraview window and I will drag and drop this spacecraft.stl file here. Okay, now we can see that this is the geometry that we saw and this is what we have got. Okay, and the z direction is like this, y direction is like this, but we will have to rotate it first so that the gravity will act negative y direction. And if you turn on the data access grid, you can see that the mesh is very small. It is in the order of centimeters, but we want it in the meters. Now we will also see how to scale the geometry to meters within OpenFOAM itself. I have already made a separate video or descriptive video on how to do this. I will drop the link in the description. You can check it out. But in this video, I'll quickly brush up on how to do those things like rotating as well as scaling up. Okay. Now we will go to our location, right click, open a terminal and type WSL. You will open our OpenFOAM here. Okay. Now you have your spacecraft.stl here. So the first task is that we have to scale up the geometry. I will use a feature called surface convert. So this function in OpenFOAM will help you modify the STL files. If you want to know more about surface convert, you can just type surface convert space hyphen help. It will give you the syntax, which is surface convert. It is taking these options and then there is an input file name and then the output file name. So that is the syntax. We are going to use this for scaling. So for scaling, we also have to give a factor. Now let's see how to do it. So surface convert, and then what we have to do is scale. Let's say we have to scale it by a factor of 100, and we also have to give the input file name. So in our case, it is spacecraft.stl. I already have this in this location, and let's say I want to make the output as spacecraft scaled.stl. Just type that command and then hit enter. It will take you to this location and your spacecraft scale.stl will be generated. You can see it here. So for the syntax to be clear, so this is the syntax. I'll also put in the description just in case if you want to copy or something. So this was the syntax that we used. Now let's see whether it has worked or not. I'll go to paraview. I'll hide this. I'll open the spacecraft scale.stl, drag and drop it here. You can see that this is definitely larger. It is going from around -6 to +6 in your y direction, and the x direction it is around again -7 to +9 or something. Okay, that's fine. But now let's say we want to keep the gravity in negative y direction. If you don't want, you can just keep it as such. But if you want to learn how to rotate an STL file in OpenFOAM, you can just see this steps. We are going to rotate it the clockwise of x direction, which is like if you see from the positive x direction, we are rotating it in anti-clockwise or the negative direction. So you can understand it through your geometry knowledge. We are going to rotate it by a factor of -90 degrees in x direction, right? So we are going to do just that. For that, I'm going to use a function called uh, surface transform points. If you want to know how this works, you can just type surface transform point hyphen help and you will get all the syntax, the input parameters and options, everything. So we are going to use this feature. We rotate X. So how do we do it? First go to surface transform points. Then we have to give our input file. What is our input file? It is spacecraft scaled.stl, and let's say the output is spacecraft rotated.stl, and we give a space and then we have to type rotate X, and now we have to give the angle. In our case it is minus 90 degrees, so I will type minus 90 and press enter. So this will take a bit of time and then it will give a new STL file which is rotated minus 90 degrees in by keeping X axis as the reference. Go here, drag and drop, click on apply. Okay, now we have a new geometry which is just the way we want it. Go to Z direction, it is the gravity is acting in negative Y direction. We can keep it like that. Even if you go to isometric, this is in proper view. So this is what I wanted and we have got this. Okay, now we will see how to generate the fluid domain. So this is the solid domain. On top of this we need the mesh. Usually in snappyhex mesh we will use the block mesh to do it, but in cfMesh either you can import it as an external STL file and then do it, or else you can use block mesh also, but the convention is different from what we generally do in snappyhex mesh. So you can see what I'm doing here and you can follow the steps. So this is what I'm personally comfortable with, or you can understand the steps and then once I generate the STL file you can follow with any other CAD software if you are comfortable with that. Okay, before confusing you any further, just watch this video entirely. You will understand the concept, then you can approach it in any way that you prefer. I'm going to use block mesh and I'm going to make the fluid domain. So I have already made a block Meshdict. I will open it. And see, I have defined few vertices. I have defined a block using these vertices, but I did not subdivide them. I just kept it as 1, 1, 1, which will just generate one phase in each side. And I have defined inlet, outlet, and watts. Now let's quickly run this block mesh and see what this offers us. I'll run block mesh. Now let's open this para.foam in our paraview. Okay, I'll go to wireframe mode. You can see that this block mesh is enclosing this aircraft, but still it is not very ideal for an external aerodynamics case. You should have substantially large fluid domain to enclose this aircraft, but for this tutorial it will take me so much time to generate the mesh with a large number of cells. So I have kept it just to enclose this geometry. Right, so this is not ideal for a simulation, but just to learn the meshing process this is okay. If I go to surface with edges, you can see that each face has only each side has only one face. Instead of subdividing we are keeping it like this. You will understand why I'm doing like this when you understand why I am doing this. Sorry if that was confusing. So what I'm going to do is I'm going to use this block mesh to generate STL files. So you see here we have our inlet, we also have our outlet, we also have our walls. These are the walls. So if you want to make these as STL files separately in a FreeCAD or Fusion 360, that's up to you. Then you can follow the process which I'm going to tell you. But I'm just using this because I'm very comfortable with block mesh for these things than using a CAD software to generate surface STLs and putting it. Everything is a bit time consuming. It's easier in block mesh, so I'm doing this. So what we are going to do is we are going to use a feature called foam to surface. So this will take certain parameters and we are going to use this function called try. So it will give a triangulated surface, and then we are going to use the mesh under our constant folder. So this is constant. If you don't put constant, it will by default take constant. Now the syntax is we also have to give an output file name. I will give patches.stl as the name. Press enter. We have our patches.stl. Okay, I'll hide this paraview. I'll just drag and drop this patches.stl here. Click on apply. You can see we have inlet separately, walls in red color and outlet in like white color. If I zoom inside, we can see the plane is just inside this. Okay, if I change this to wireframe mode, you can see that the plane is inside and the block mesh is outside, but these are just STL files, right? But how do you understand what is happening here? If you open this patches.stl in your Visual Studio Code or Notepad, you can see that these are just bunch of numbers defining these faces. It is starting as solid inlet and solid inlet, and it is like solid outlet and end solid outlet. Similarly, we have our solid walls, right? It is ending with solid. Similarly, if you just open your spacecraft rotated in your VS Code or Notepad, you can see that again it is the same thing. It's just bunch of numbers defining these STL files. By the way, this is in ASCII, that is why it is working. If it is in binary, first you have to convert it to ASCII. I have another video on how to convert any geometry from any STL geometry from binary to ASCII. You can check that video. I'll give the link in the description. So here you can see the name of the solid is patch 0, and in the end solid also you can see that it is patch 0. So I'm just going to change this as spacecraft. I'll copy this just so that I won't make any mistake in the naming. It is case sensitive, so I'll copy and paste it here. So we have solid spacecraft and then it is ending there. Okay, I'll close this. Now what we have to do is we have to merge these. We have our patches.stl. We also have our spacecraft rotated, but we have to merge these into a single STL file so that we can use it. Now this is where if you are using CAD software to generate STL files, you have to follow from here. You have to merge these STL files into a single file so that you can use it under your cfMesh. So how do I do it? I'll take the spacecraft rotated.stl, which was our finalized geometry. I'll copy paste and then I'll rename it as geometry.stl. I'll open this geometry.stl. Maybe go to the last line. Okay, and what I'm going to do is I'm also going to open my patches.stl here. I'll copy this entire patches.stl and paste it in the last line. You leave a space or not, it doesn't matter. I just want to split it, so I'm splitting it like this. I'll save the geometry.stl file, close it. Now this will merge it. Okay, so how do we verify? I'll hide all of these here. I'll just drag and drop our geometry.stl alone. So you can go to your wireframe and see that it has been merged. Right? It has been merged. So inside the same geometry.stl, you have multiple patches. You have inlet, you have outlet, you have walls. You also have your aircraft or the spacecraft, with each having its own different name. So this will be helpful in defining patches, adding refinement region, adding boundary. Everything under cfMesh depends on the name of your patch. So this is very essential. So if you used any external CAD modeling software, then you can follow the same step to combine multiple STL files, like combining inlet to outlet, then that to walls, and then that to this aircraft, anything. So you just understand the concept. Now you can follow along and you can do. So once we generate the STL files, our geometry preparation is done. We don't have anything more. For a cfMesh to work, we only need this geometry.stl. So what I'm going to do is I'm going to create a folder called geometry, and I will just cut and paste everything here just to keep the case clean. I will copy the geometry.stl alone and put it here. So this has to be in this location along with your constant and system. Okay. Now when you install cfMesh, you will get these folders. Under tutorial, there are two ways of generating 3D mesh. One is state mesh, another is Cartesian mesh. If you open their documentation, you can understand it better. So this will be your Cartesian mesh, mostly hex meshes, and you also have your tetrahedral mesh, which is like triangulated. So we are going to use Cartesian mesh in this, but the process is the same. Instead of the command Cartesian mesh, you have to use state mesh. That's it. There is no other change. So what I'm going to do is I'm going to take the Cartesian mesh bunny octree. Under system, you will have this Meshdict file. I have copied that and put it in my system directory, and I have modified it a little bit just to suit my case. So now let's see how the case setup works for Meshdict. It's If you have worked with snappyxmesh previously, this Meshdict is similar to snappyx Meshdict. This is where we will configure our mesh parameters. So initially, I'll just comment all of these, pretend as if these lines don't exist here. We are interested only in these two. First, we have to give input. Oh, don't worry that it is in FMS. We will see what that is. First, I will save this. And let's say initially our mesh size is 1 because ours is in the order of meters, right? -6 to +6 and all. So this will be very coarse mesh. It's a very bad mesh, but we will just see what it does. Now we have given the input parameter .stl and the mesh cell size as 1. If you go to the documentation and check the syntax, they have mentioned that these two are mandatory settings. The surface file and the maximum cell size or mandatory parameters. If you want to add more, you can add boundary cell size and these things. You can check the documentation. You will be adding boundary layers as well and doing local refinement also in this tutorial. But right now, only these two lines matter. We are inputting geometry.stl and the maximum cell size is 1. I'll save the file. Go to your location. Just ensure that you are in the location where you have geometry.stl constant and system. Then the command you have to do is Cartesian mesh. Enter, and you just wait for the mesh to run. Once it is done, we can look at the mesh. By the way, if you are enjoying this video, consider subscribing to the channel. If you like this video, just drop a like. If you have any questions or suggestions, you can drop down in the comment section. It will be very helpful for me to make more useful videos for you guys. So now the meshing is done. You just do check mesh. You can see that the mesh is saying it is okay. But is it really okay? That is what we are going to see now. I will open the mesh in para.foam or the para view. I'll click on apply and leave this as spacecraft alone. You can see that this is pretty bad mesh and the corners are not sharp. We have very bad cells. It's not nice at all, right? Yeah, so if you just see the aircraft, it's not even looking like an aircraft. It's nothing good. So this is what you are getting for maximum cell size of 1 meters. And I'll also insert a clip plane so that you can see things better. So this is the kind of mesh which we are having. It's not good at all. Now let's go further down and we will refine it further. Let's go to 0.5. I'll save this file, run the Cartesian mesh again. Now let's wait for the mesh to end. It will be much faster than snappyx mesh. So if you worked with snappyx mesh, you know how long it takes to generate a mesh like this, but it was much faster here, right? Refresh, we got a better mesh there. Refresh this, got a better mesh. Yeah, this is definitely better, but you can see that the angles are not sharp, right? These angles are not sharp. So how do you make this better? That is where a format called FMS comes in. Now we will look at what FMS is. If you go to their documentation, you can see that they are advising us to use FMS because that holds the surface angle parameters properly. So now let's see how to convert our STL to our FMS file. Okay, the command is surface feature edges, and if you go to help, it will give you all the parameters which you have to give. And what we are going to use is the angle. So I will type in the angle, and we want an angle of, let's say, 5 degrees. Usually 10 is fine, but 5 is very good. You can use 5. Actually, the smaller the better. This is the deviation from which you are deviating from your original STL file. I will keep it as 5. Then you have to give the input file name. So our input file name is geometry.stl. Let's say our output file name is geometry.fms. Then press enter. Wait for the process to end. Once the process is ended, you will get this geometry.fms. So this file is not openable in your paraview, but you can still open and see what it is like in your VS Code. It is very similar to STL files. This is just bunch of coordinates. You go at the end, it is just bunch of coordinates all along. right? So now here we will change it to FMS in our Meshdict file, and I will run the Cartesian mesh again. Okay, now the meshing is done. We can do check mesh thing, okay, but we can't trust check mesh. So let's check it visually. You can see that the corners have improved. Similarly, if you go to this, you can see that the corners have definitely improved. That is what we wanted and we have achieved it. But still this mesh is really bad. So we will go with refinement, okay. So we will first change the maximum cell size to 0.25 instead of 0.5. We'll run the Cartesian mesh again. Okay. Now the meshing is done. You can go here, um, refresh it. Yes, it's better. Refresh this. Yes, it's better. So this geometry looks much better, even though we have faulty edges at the end. But we will add local refinement to this zone, because if we start refining everything, then it will be a problem. Computationally, it will become very expensive. So we'll just add local refinement. If you go to the documentation and if you scroll down, you can see that they have a function called local refinement. The mandatory patches, like you have to give the patch name. Inside that, you can choose to give additional refinement levels, and you can also give subset cell size, but this is optional. And we are going to use only these two parameters, not the cell size. I'll go to my Meshdict and comment this. See, we have our spacecraft as the patch here, because you can see here that is the name here. We'll use spacecraft, and the first, let's keep the additional refinement level as 1, and maybe just to demonstrate I will keep this as 0.0001. So this is refinement thickness is how far away from your geometry till how far you need the refinement. Okay, initially let's just keep it as 0.0001, but I want to keep it as just 0. Let's run the Cartesian mesh again, and now you will see how it gets better. Okay, now the meshing is done. I go here, click on refresh. You can see that it has refined till certain area, and it has refined our geometry as well. This is like much better now. Okay, but now I want to just keep it as 0. Let's assume that we want to keep it as 0. In fact, we can add a refinement box if we want. We can add refinement in our trailing edge. Everything can be done, but let's say for this tutorial, let's keep it simple. In another tutorial, I will explain all those as well, and a TED mesh as well. So stay subscribed for those things. I will keep this as 0 and I will put this as 2. Save the file. I'll run the Cartesian mesh again. Now mesh is done. I will refresh it. You can see this is much refined. Refresh this. You can see the refinement is not very far from the refinement zones. Right. Like this is much cleaner. And you also have captured the features properly. That is very nice. In fact, you can refine much finer, or you can add local refinements. Everything can be done. But this is fine for me for this tutorial, because we also have to add our boundary layers. If you go to the documentation, you can actually create few boxes if you want to try, or else wait for the tutorial. Yeah, I will add it in the next video. And if you just scroll down further, you will find boundary layers. Yes, so we are going to add the boundary layers. So these parameters are optional, and you have to define the name and the number of parameters. Everything is just optional, and I have made it very concise. Made this function. Let's uncomment it. Typo. Okay. Our patch name is spacecraft. The patch boundary layers is the function. We are going to add 3 layers with the thickness ratio of 1.2. I'll save this file. Go here and we run the Cartesian mesh. Let's wait for the mesh to end. Okay, the meshing is done. So let's go here, refresh it. You can see the boundary layers here, right? So the boundary layers has been added. If you want to add any more controls, you can check these parameters, and you can add your first layer thickness also. If you calculate your y plus, everything can be done. You just have to modify extra parameters here, and that will do. Okay, now that we have generated the mesh, there is one last thing that has to be done. Whenever you generate the mesh, just do this: renumber mesh and overwrite. So this will reduce the band of the mesh which is there, and this will make the computation faster. Okay, now let's do check mesh. Okay, we have around 0.8 million cells and everything is fine. So this is the case setup for Cartesian mesh. So that's it for this video. In the next cfMesh video, I will explain how to run TET-mesh, how to add refinement boxes, and how to run cfMesh in parallel. So consider subscribing to the channel. If you enjoyed the video, drop a like. If you have any questions, comment down. Bye bye.